Hi folks, in this video we're going to talk about translation into Bool. There's something that's important that's lost in translation to Bool. So when we translate from English to Bool, I want you to understand that it's not going to be perfect. That doesn't mean that it's useless. So our logical systems like Bool can do all sorts of impressive things, like prove certain arguments are valid, prove certain arguments are invalid. But that doesn't mean that they perfectly capture their natural language counterparts like English. For example, there's a lot in English that is not truth functional, but Bool then just can't capture it because Bool is a truth functional logical system. Let me give you an example of this. We saw that this symbol, the double bar, double arrow, this means logical equivalence. So it's a fact that D and C is equivalent to C and D. This is called the law of commutativity. It's just like in algebra where you have 1 plus 2 is equivalent or equal to 2 plus 1. So order doesn't really matter in the symbols like conjunction or in the symbol like disjunction. Now you can prove this equivalence holds by doing a truth table for these two sentences, and you're going to see that they have the exact same truth function. So truth tables, you can now see something truth tables can do. They can prove things are equivalent. That's very powerful. That's a powerful fact about truth tables. But when we translate things into Bool, we're going to lose stuff that maybe messes up this equivalence. Let me give you an example. Let's say that I have two friends, Pia and Alberto. And here's a sentence. Alberto asked Pia to dance, so D for dance. And Pia started to cry, C for cry. Now look at what the sentence says. Alberto asked Pia to dance and Pia started to cry. Now that sounds like Alberto is the villain in that sentence. But look if I just reverse those. Pia started to cry and Alberto asked Pia to dance. See, in this one, Alberto is the hero. So in English, these things don't necessarily mean the same thing. These could mean very different things to your audience. So the order might matter quite a lot in the English significance, but we lose all of that kind of thing in Bool because that order is not truth functional. We don't capture that order because in terms of the truth functional content of these, order doesn't matter. So in English, there's going to be lots of nuance we might miss when we translate things into Bool. But again, like I said, that doesn't mean Bool is useless. It just means we have to recognize its limitations so that we only use it for its intended purposes. There are all sorts of things that are equivalent in Bool that are going to give Bool lots of power. Some of these are just famous and well known enough that they're given names. It's not like there's anything magically special about these equivalences. They just turn out to be really useful ones, and they've been studied for hundreds of years, so they have special names. Like double negation. I can just drop two negation symbols, and that's the same thing as P. Or any even number of negation symbols is equivalent to just the original sentence. That's just a really important and helpful law that we can use. De Morgan's laws, these talk about how to push a negation symbol onto one of the other Booleans, either a negation, either a conjunction or a disjunction. So when I distribute negation onto a disjunction, I put the negation on each of those disjuncts, but I have to flip it to a conjunction. And similarly, if I push it onto a conjunction, it gets flipped to a disjunction. These De Morgan's laws are also really common laws in Bool, and it's essential to know and understand them. Notice this again helps you understand those translations of neither nor. So if that was confusing for you, you can see here why these two translations of neither nor were both good, because neither P nor Q could be translated this way with the negation's narrow scope, or it could be translated this way with the negation wide scope. But those are the two equivalent translations for neither nor. Now, besides proving things are equivalent with truth tables, you can also use truth tables to prove sentences are not equivalent. So here's your job for this video. Pause your videos now and see if you can prove that these are not equivalent. What would that take? I'll give you a hint. You need to compute the truth functions for them. So pause your videos now, compute these truth functions. Okay, that was your chance. Last chance to pause your videos. All right, now I'm going to show you what the truth functions look like. In canonical form with three sentences, remember, they have to go in alphabetical order, and it's the one that's furthest to the right that alternates TF, TF. The next one's going to alternate in pairs, TT, FF, TT, FF. The next one's going to alternate in fours, TT, TT, FF, FF. If we had another sentence over here, like O, then this would have 8 T's and 8 F's. So you're always increasing by the power of 2. Now, here's my two truth functions. The main connective is this thing. Here's the main connective of the disjunction is wide scope. So here's the first one's truth function. I just computed this to help you see how I got the main connective. Here's the main connective of the second one. So these are the two columns to compare. And look, They're equivalent on many of, they have the same values on many of these rows, but look at this. On row 5, their values are different. On row 7, their values are different. So the answer, which row proves they're not equivalent, you could have said 5 or you could have said 7, or you can say 5 and 7. All you need is a single counterexample, a row on which their values are not identical, and that alone proves, that's enough to prove that they're not equivalent, because equivalence requires that they have the same value on every single row. Notice what this example shows you too. Remember we said a long time ago that if you have a mixture of Boolean connectives, you need parentheses for grouping. So this proves to you that grouping matters, that having P and Q grouped together is different than having Q or R grouped together in these sentences. So if you have a mixture of ands and ors, you have to have parentheses to disambiguate. Otherwise, it's not clear what you're actually saying. What else can you do with the truth table? Let me just mention one other set of concepts that you're familiar with. So you know logical truths are true sentences that are always true. We can now use a truth table to prove that certain sentences are logically true. We just prove that it's true no matter what on every row of its truth table. And we're going to call those sentences tautologies. Like compute the truth function for the sentence P or not P. You'll see that that sentence is true no matter what. So it counts as a logical truth. Tautology is one type of logical truth. Truths, namely, that have T's in its truth, just T's in its truth function. Analogously, a tautological falsehood is a sentence with all F's. This is a type of logical falsity. It can't possibly be true because its truth function is all F's. Contingent sentences, remember, we said that those could be true and they could be false. So we can use the truth tables to also capture this concept. If a sentence, if its truth function is true on some rows and false on other rows, then it's merely contingent. Like look at those sentences we just computed. This sentence is true on some rows and false on some rows. So this would count as a contingent sentence because it's possibly true, possibly false. Now, what is its actual truth value? Because we know it's possibly true or false, is it really true or really false in the actual world? That depends on what row we're on. So these atomic sentences are going to be either on true or false depending upon what the world is like and depending upon what they mean. So maybe PQR means Pia, Quinn, and Raquel are guilty, and maybe the real world is row 3, where Pia and Raquel are guilty, Quinn is innocent. Well, what that means is this sentence is actually true. So the actual world is just one of these particular rows. But the whole profile of the sentence, its truth function, is this whole pattern, and that's what determines whether it's contingent or not, whether it's possibly true or possibly false. Regardless of whether it's just actually true, it's possibly false. And that's why that sentence is contingent. Okay, thanks.